Welcome to the Deep Dive, where we take a stack of information articles, research, your own notes, and extract the most important nuggets of knowledge. Our mission is really to give you a shortcut to being truly well-informed with some surprising facts and hopefully just enough humor to keep you hooked. This Deep Dive is brought to you by EasyMasterAI.com. Today, we're embarking on, well, an in-depth exploration into the fascinating and really rapidly evolving world of artificial intelligence. Specifically, we're unpacking the profound insights from a pivotal new publication, AI Engineering, Building Applications with Foundation Models by Chip Huyen, published by O'Reilly Media. This work offers a really comprehensive look at the end-to-end process of adapting these advanced AI models to solve real-world problems.
Such a timely discussion, isn't it? I mean, I remember when tools like ChatGPT first emerged, there was this genuine sense of disorientation for a lot of people. The sheer power of these models surprised many. But for those of us, in the AI community, we kind of knew scaling up models generally improved them.
Yeah.
What truly shocked us, though, was the explosion of new applications these capabilities unlocked. It really felt like a completely new field was born almost overnight. AI engineering.
I completely agree. So for you, our curious listener, consider this your essential guide. We're going to try and understand what AI engineering actually is, how it fundamentally differs from, say, traditional machine learning, what incredible things it can potentially do, and all the practical challenges and ingenious solutions involved in bringing these powerful models to life. It's a huge topic, yeah, but we're going to make it accessible and hopefully pretty interesting. All right, let's jump right in then. The book really emphasizes this big shift. What's the core idea behind this new frontier of AI engineering?
Well, what's fascinating here is that the fundamental idea has kind of flipped. AI engineering is primarily about adapting models that someone else has already gone to the trouble of training. You're not typically starting from scratch to build your own model anymore, which is, a significant departure from traditional machine learning or ML engineering.
That makes a lot of sense. So in traditional ML, the flow was usually collect your data, then train your model, and finally build your product. The focus was really heavily on the modeling and the training part. How does AI engineering change that specific flow?
Precisely. In AI engineering, that sequence is often inverted, or at least started differently. You might start with a product idea first, then you figure out the data you need, and then how to adapt an existing model to fit that product.
Ah, okay.
This completely changes the pace of development. It rewards incredibly fast iteration, allowing companies to prototype and maybe even ship AI products in like weeks or months, rather than the years it might have taken previously. That's a massive strategic advantage, obviously.
That's a really powerful shift. And the book highlights that this new approach, and well, it deals with much bigger models, right? Models that consume far more computing resources and can incur higher latency. So this isn't just a conceptual tweak. It means you need entirely new solutions and probably more powerful hardware to manage that scale. It's a whole new infrastructure challenge.
It absolutely is. And to simplify things a bit, any AI application fundamentally consists of three layers. You've got application development, model development, and infrastructure. Now, while all three are essential, the book's perspective and kind of our focus today really leans into the model adaptation aspect within that model development layer. That's where a lot of the specific engineering magic happens now.
Now, here's where it gets really interesting for me. The probabilistic nature of AI. Unlike, traditional software that gives you a deterministic output every single time, AI outputs are predictions based on probabilities. They are not guaranteed to be correct. And this probabilistic nature is a bit of a double-edged sword, isn't it?
It truly is, yeah. On the pro side, this makes AI great for creative tasks. Think brainstorming unique ideas, generating captivating designs, or even writing fiction. It allows AI to sort of explore beyond common paths, to be genuinely imaginative in ways a deterministic system just couldn't be.
But on the con side, this very nature can be incredibly frustrating for tasks requiring absolute precision. It leads to what the author calls inconsistency. And that inconsistency can show up in a couple of ways, right? First, you might give the exact same input to an AI model twice, say, asking ChatGPT to score an essay, and one time it gives you a 3 out of 5, and the next time, maybe a 5 out of 5.
Right. It's like a judge who can't quite make up their mind. And the second way is when a slightly different input, maybe just capitalizing a letter or rephrasing a word slightly differently, leads to drastically different outputs.
Yeah.
This can be genuinely disorienting for users who expect predictability.
It's like when you ask a human for directions, you expect them to give you pretty much the same answer twice. even if you phrase the question slightly differently. If they started telling you to go north 1 minute and south the next based on a tiny change, you'd be utterly lost, right?
Exactly.
Users expect similar consistency from AI, and when they don't get it, it really breaks that sense of trust. We've talked about the new approach to AI engineering and this inherent probabilistic nature, but what are these powerful models we're adapting? Let's dive deeper into their core building blocks.
Right. So we're talking about what's broadly termed foundation models. This is kind of an umbrella term encompassing everything from large language models or LLMs, like the engines behind ChatGPT, to the newer large multimodal models or LMMs.
What's truly fascinating is just how rapid the evolution has been here. We've moved from these really narrow task-specific models. I mean, imagine a model trained only for sentiment analysis or only for translation to these incredibly general-purpose models. An LLM, for example, can now often do both sentiment analysis and translation right out of the box, sometimes with remarkable accuracy.
And the innovation doesn't stop there. We're seeing the rapid rise of these multimodal models like GPT-4v and Claude 3. These models can understand and process information across different data types simultaneously, images, text, even video in some cases. This ability to sort of cross-reference and connect information from multiple senses makes them even more powerful, opening up entirely new possibilities for applications.
So when we talk about a model's performance, what are the fundamental ingredients? The book really distills it down to 3 core pillars, which is helpful.
Indeed. The first, and you could argue the most critical, is training data. And here, the book talks about the 3 golden goals: quantity, quality, and diversity. You need enough data, it needs to be good, clean data, and it needs to represent a wide range of information and perspectives.
And here's a truly surprising fact from the book that jumped out at me. A small amount of high-quality data can actually outperform a large amount of noisy, low-quality data. They mentioned the Lima model, a 65 billion parameter model, fine-tuned with just 1,000 carefully curated examples, performed comparably to GPT-4 in 43% of cases as judged by humans. Does that kind of challenge the bigger is always better mindset we often hear about in AI?
It absolutely does. And it's a really critical insight for anyone building these systems. It emphasizes that what you feed the model can be even more important than how much. We also see this challenge play out with multilingual performance. GPT-4, for instance, is significantly better at math and English than in languages like Armenian, Farsi, Burmese, or Amharic. It actually failed all 6 math questions in Burmese and Amharic in one study. This points not just to underrepresentation in the data, which is part of it, but also to the subtle structural differences between languages that models struggle with.
This also sheds light on why proprietary data, things like copyrighted books, unique translations, internal company contracts, or specialized medical records, is becoming such an increasingly valuable competitive advantage in the AI race, right?
Definitely.
Companies like Reddit and Stack Overflow have changed their data terms to prevent scraping, making unique, high-quality, human-generated data more scarce and therefore more valuable for training better models.
The second pillar is model architecture. As of now, the transformer architecture is largely dominant, especially for language-based foundation models. Its strength comes primarily from its attention mechanism, which uses something called query, key, and value vectors.
Okay, and for those of us who aren't deep in the ML weeds, what exactly does that attention mechanism do, in simple terms?
Think of it like the model's selective focus. When processing a sentence, these query, key, and value vectors allow it to figure out which words or parts of the input are most important to pay attention to when trying to understand another word's meaning or predict the next word. It's kind of why transformers are so good at understanding context across long stretches of text.
That's a great way to put it. However, a key limitation with this architecture, as the book points out, is how hard it is to efficiently extend its context length, basically. How much information it can consider at once without performance degrading or costs skyrocketing.
Exactly. While transformer-based models still dominate, the book mentions alternatives like RWKV, which is an RNN-based model, that are trying to overcome these context limits. Although their real-world performance at truly long context is still an active area of research and development.
Got it. And the third pillar?
The third pillar is model scale. This can be defined by 3 key numbers: the number of parameters, which is sort of a proxy for the model's learning capacity, the number of training tokens telling you how much data the model actually learned from, and FLOPs, or floating point operations, which basically a proxy for the sheer computational cost of training the model.
And when we talk cost, we're talking serious numbers. The book gives an example. Training GPT-3 with its 175 billion parameters, cost over $4 million, and that's assuming pretty good 70% utilization and $2 per hour for a single H100 GPU. That's a massive investment just to get the base model trained.
It really is. And on the flip side of scale, there's also this counterintuitive finding called inverse scaling, where sometimes more alignment training, which is meant to make models better behaved, can actually lead to them expressing undesired behaviors more strongly, like certain political or religious views.
That's weird. So trying to make them better in one way can unpredictably make them worse in another. It's a paradox, yeah. It shows alignment is complex. Once these large models are initially pre-trained, they're really optimized for just completing text, not necessarily for having a helpful conversation. And if you just let them generate text indiscriminately, they can produce problematic, biased, or just plain unhelpful outputs. So the goal of post-training is absolutely crucial. It's all about making these models helpful, harmless, and honest.
And to achieve that, the book details some key techniques. One is supervised fine-tuning, or SFT. How does that work?
SFT is like giving the model direct, correct examples of how to follow instructions or answer questions. Think of models like InstructGPT. You show it thousands of examples of good prompts and good responses. Do this and do that, answer this question like this. It's essentially teaching the model what a good response looks like by showing it many, many examples.
And then there's preference fine-tuning, often referred to as reinforcement learning from human feedback, or RLHF. That sounds a bit more involved. It is, yeah. This is where models are trained to align with human preferences through comparative evaluation. Imagine presenting the model with two possible responses to a prompt and having a human judge simply say, I prefer this answer over that one.
Ah, okay. Not necessarily right or wrong, just better.
Exactly. This teaches the model what humans genuinely like or find more helpful, even if there's no single correct answer. Think of it as refining the model's taste or its conversational manners. It's often the cherry on top that makes a model truly feel helpful, engaging, and aligned with user expectations.
It's truly incredible how quickly AI has integrated into so many aspects of our lives and businesses. The book highlights that the number of potential applications seems almost endless, and even just categorizing them is a challenge in itself, as different surveys use different approaches.
That's right. It's moving so fast. But the book does a good job of breaking down some broad use case categories. For enterprises, for example, we're seeing AI applied to customer experience, trying to boost employee productivity, and optimizing complex business processes.
And for consumers, the applications are everywhere, aren't they? Programming assistance, data analysis, customer support, marketing copy, research help, web design tools, and even creating, frankly, stunning art. What's interesting is how many applications can actually belong to multiple categories. Like a bot, for example, could provide companionship and aggregate information simultaneously. It's really blurring those lines.
Definitely. Let's maybe do some key application deep dives, starting with coding. This is hands down the most popular use case in multiple generative AI surveys. Why? Well, AI is proving to be remarkably good at it, and the early adopters are naturally coders themselves, so they jumped on it quickly. It's been a really rapid integration.
And it's generating real revenue, too. Examples like GitHub Copilot are apparently generating over $100 million in annual recurring revenue already. The book mentions AI can potentially double productivity for writing documentation and improve code generation or refactoring tasks by 25–50%. That's significant.
Yeah, huge gains. It also notes it seems to be notably better at front-end development compared to highly complex back-end tasks, which kind of makes sense, as front-end often involves more recognizable patterns and boilerplate code.
Okay, what about image and video production?
This is another area where AI's probabilistic nature, that creativity we talked about, really shines. We've seen massive success stories like Midjourney, which reportedly generated $200 million in annual recurring revenue in just 1.5 years.
Wow.
And there are other big names like Adobe Firefly, Runway, Pika Labs, and now OpenAI's Sora for video.
It's a clear trend. The book mentions that by late 2023, half of the top free graphics and design apps on the Apple App Store already had AI in their names. It's a pretty good bet that soon AI capabilities will simply be a default feature in these apps, and they won't even need to advertise AI anymore. It'll just be how they work.
Writing is another really natural fit. I mean, AI has long aided writing, from basic autocorrect to autocompletion. It's an ideal application because, well, we write a lot, it can often be tedious, and we generally have a relatively high tolerance for small mistakes or imperfections in early drafts. The author of the book even found AI very helpful for brainstorming fiction ideas, for instance.
However, there's a really critical concern raised by the author here that paints a potentially, well, bleak future for internet content quality. AI's proficiency in SEO, search engine optimization, has enabled a new generation of content farms. These are basically junk websites filled with low-quality AI-generated text purely to drive ad traffic.
Yeah, I've seen some of that. It's concerning.
NewsGuard, for instance, identified almost 400 ads from 141 popular brands running on these kinds of sites, with one farm apparently churning out 1,200 articles a day. The author warns that if this isn't reined in, the internet could soon be absolutely swamped with untrustworthy AI-generated content, potentially making us distrust everything except the most established human or brand sources. That's a significant worry for the whole digital landscape.
Moving to education. We've seen a truly rapid shift, haven't we? From an initial sort of knee-jerk reaction of banning tools like ChatGPT in schools.
Right, I remember that panic.
To schools now figuring out how to embrace them. Initial fears of cheating led places like New York City and Los Angeles public schools to ban ChatGPT. But they reversed those decisions just months later once they saw the potential upsides.
Yeah, instead of just banning, AI can be incorporated to help students learn faster and maybe more effectively. It can summarize dense textbooks, generate personalized lecture plans tailored to individual learning styles, whether you're an auditory or a visual learner, and even translate things like math equations into code for students who prefer that approach.
Exactly.
Yeah.
And AI can generate practice quizzes, act as a debate partner on complex topics. Khan Academy's AI assistants are a great example of this. The impact is pretty significant. The book notes that Chegg, a traditional homework help company, saw its share price plummet as students naturally turned to free or cheaper AI tools for assistance.
Then there are conversational bots and AI agents. This goes beyond just text-based systems like ChatGPT. We have voice assistants like Siri and Alexa, and even more immersive 3D conversational bots starting to appear.
Yeah, and a fascinating application the book highlights is smart NPCs, or non-player characters, in video games like The Sims and Skyrim. Using AI allows for far more intelligent and dynamic interactions with game characters than traditional scripted behaviors ever could. It makes those game worlds feel much more alive and unpredictable.
That sounds cool. Finally, information aggregation and workflow automation. AI truly excels at distilling complex ideas and summarizing information. Apparently, 74% of generative AI users use it for this very purpose.
Makes sense. It's a huge time saver.
And it can automate repetitive tasks across enterprises, things like lead management, invoicing, or basic data entry. An especially exciting use case mentioned is using AI models to synthesize new training data, which can then be used to improve the models themselves, creating this kind of powerful, self-improving feedback loop.
Right, using AI to make AI better.
Ultimately, the book makes it abundantly clear. It's relatively easy these days to build a cool demo with foundation models. You can get something impressive up and running pretty quickly. But it's hard to create a profitable, robust, reliable product. And that's where the absolutely crucial processes of evaluation, adaptation, and performance tuning come in.
Evaluation is just vital throughout the entire AI application lifecycle. It's really how you mitigate risks and uncover opportunities from the moment you select a model all the way through deployment and ongoing monitoring. However, a key challenge, as the book stresses, is that evaluating foundation models is far harder than traditional software because of their open-ended nature.
Oh, so?
Well, unlike, say, fraud detection, where there's usually a clear right or wrong answer, a chatbot has infinitely possible valid responses. It's impossible to curate an exhaustive list of perfect ground truths to compare against.
This challenge has led to this interesting, maybe slightly meta concept of AI as a judge, where AI models are actually used to evaluate other AI outputs. What are the pros and cons of using an AI to critique another AI? Seems a bit like the fox guarding the henhouse, maybe.
Well, there's some truth to that concern. The clear pro is that AI judges are much cheaper and faster than using human evaluators. You can scale your evaluations dramatically. But there are definite cons. AI judges, like all AI applications, are probabilistic and prone to their own biases.
Like what?
Well, one is inconsistency. The same AI judge with the exact same input can output different scores if you run it twice. Another is position bias, where AI judges often favor the first answer they see in a comparison, which is interestingly the opposite of human recency bias. And then there's verbosity bias, where they might favor longer answers even if those answers contain factual errors, though newer models like GPT-4 seem to be getting a bit better at avoiding that last one. It just shows you have to be really careful how you design and use them.
Okay, so when it comes to the key evaluation criteria for these applications, beyond just avoiding bias in the judge, What are some of the non-negotiables the book highlights? What absolutely needs to be checked?
There's functional correctness, for example, making sure any generated code or SQL database query actually works, like unit tests in traditional software engineering. Then there's factual consistency, trying to verify if the AI's outputs align with explicit facts provided or known truths. This is especially challenging given how much misinformation is on the internet, which is why benchmarks like truthful QA are so important for testing this specific capability.
And beyond just, is it factually right? What about the more qualitative aspects? Like, is it behaving well?
All right. Another key area is detecting harmfulness and bias, ensuring outputs aren't toxic, hateful, or generating inappropriate content, or exhibiting unwanted political or religious biases. And finally, instruction following. How well a model adheres to specified formats or content constraints you give it, like asking for a JSON output, or a response with exactly 3 bullet points, or telling it not to mention a certain topic. It's about ensuring the AI understands and respects the boundaries you set.
The book also discusses the challenge of benchmarks themselves. We see all these public leaderboards popping up. What are the pitfalls there? Are they reliable?
They can be useful, but you have to be cautious. Public benchmarks can become saturated, meaning the best model scores so high it becomes hard to differentiate their actual performance.
Yeah.
And even more problematic, models can be contaminated.
Contaminated. How?
It means their training data inadvertently included the benchmark questions and answers itself. So the model isn't reasoning, it's just regurgitating answers it saw during training, leading to artificially inflated scores. Leaderboards, like the one on Hugging Face, are constantly trying to update and address this, moving to more challenging tasks like Math Level 5 to replace easier ones like GSM-8K that models have basically memorized. It's a continuous arms race to create meaningful evaluations.
Okay, so if benchmarks have issues and evaluation is complex, how do you actually get the model to do what you want for your specific use case reliably? That's where prompt engineering comes in, right? What's the art and science behind crafting effective instructions for these models?
It's truly both, yeah. It's an art form in figuring out the phrasing, but also a science in testing what works. It requires understanding how robust a particular model is to minor changes in your prompts. Best practices generally include being very specific, providing concrete examples, often called few-shot prompting, where you show it an example or two of what you want, and explicitly defining the output format you need, like demanding JSON output or telling it no preambles, just the answer. It's really about being as clear and unambiguous as possible with your digital assistant.
And there's a particularly powerful technique mentioned called chain of thought or COAT prompting. How does that boost performance? It sounds simple.
COAT prompting is deceptively simple, but incredibly effective, especially for complex reasoning tasks. You basically just ask the model to think step by step or explain its decision before giving you the final answer.
So you make it show its work.
Exactly. Like asking a student to show their work on a math problem. This forces the model to break down the problem into intermediate steps, which significantly boosts its performance on tasks requiring logic or multi-step reasoning. You often get a better, more reliable answer that way.
But with the power of prompts comes risk. The book explores prompt hacking and defensive measures. Expert, what are some of the ways these models can be exploited through clever prompts, and what are companies doing to protect against that?
Oh, the risks are definitely real and evolving. They range from generating misinformation or harmful content to causing service interruptions or creating massive brand risk. Like, remember when Google AI search briefly urged users to eat rocks, or Microsoft's early Tay chatbot went completely off the rails?
Yeah, those were bad.
Attackers use methods like reverse prompt engineering, trying to trick the model into revealing its underlying system prompt or instructions, or obfuscation, using deliberate misspellings or special characters to bypass safety filters. There are even automated attacks, where people use other AI models to act as attackers and probe for vulnerabilities much faster than a human could. It's a constant cat-and-mouse game between attackers and defenders.
Then there's the risk of data extraction or memorization. What does that entail? Is it easy for someone to just ask the model for sensitive data it was trained on?
It's a valid concern, especially for larger models, which tend to memorize more. Studies have shown that while technically possible to extract snippets of training data, it's generally difficult unless the attacker knows the exact or very similar context in which the data appeared during training. It's not usually as simple as just asking, tell me someone's credit card number, but it is a privacy risk that model providers have to guard against, often by filtering training data.
And a more direct, perhaps more immediate concern for companies building on these models is copyright regurgitation.
That's a big one, yeah. Models can unintentionally output text or code that is very similar or identical to copyrighted material they were trained on. This can lead to serious and costly lawsuits. Even if a model slightly modifies copyrighted material, like, say, writing a story about Randolph the Wizard that sounds suspiciously like Gandalf from The Lord of the Rings, it still poses a non-trivial legal risk for the company deploying that model. It's why careful data curation and filtering are so important.
So given all these potential attacks and risks, what are the defenses? How do you protect your AI application?
Well, there are multiple layers. Measures include establishing a clear instruction hierarchy for safety, like OpenAI does, where safety instructions override user requests. You can use prompt-level defenses, literally writing instructions like do not return sensitive information or do not discuss harmful topics directly into your application's prompts. And sometimes even simple tricks work, like repeating the core system prompt twice, once before and once after the user's prompt, just to continually reinforce the model's guardrails during the conversation.
Despite all this sophistication in prompting and defenses, models still have these fundamental limitations, like limited context windows and this tendency to hallucinate or make things up when they lack specific information not present in their original training data. So how do we give them more relevant, up-to-date context to reduce those hallucinations? That's where RA, or retrieval augmented generation, comes in, right?
RE is a real game changer for accuracy and relevance. It essentially allows the model to pause, go look things up in an external trusted data source, maybe your company's internal knowledge base, specific technical manuals, a collection of recent news articles, whatever you provide, retrieve the relevant information, and then use that retrieved information as context to generate its answer.
So it's like giving the AI open book access for its exam.
Pretty much. This significantly improves accuracy and dramatically reduces hallucinations because the model isn't just relying on its potentially outdated or incomplete internal knowledge. It has fresh, specific facts to draw from for that particular query.
And there are two main retrieval methods the book details for finding that external information. How do they differ?
Right. First, there's term-based retrieval, like the classic BM25 algorithm. This uses simple keyword matching. It's straightforward and fast, but can easily miss the semantic meaning. For example, searching for Transformer architecture might retrieve documents about the Transformers movies instead of the AI concept.
Okay, not ideal.
Not ideal.
Yeah.
Second, there's embedding-based retrieval, often called semantic retrieval. This uses vector databases to find documents whose meaning, represented as numerical vectors, aligns closely with the query's meaning. This is much more sophisticated and allows the model to understand the nuance of your question.
So if you're asking about a large language model, it'll find documents about LLMs or related concepts, not just documents that happen to contain that exact phrase.
Exactly. It understands the concept. And within RA systems, people use various strategies like chunking, splitting large documents into smaller, more focused pieces for retrieval and re-ranking, which might use a combination of retrieval methods or a secondary model to refine the search results and ensure you get the most relevant snippets of information to feed into the final generation step.
Okay, taking R8 a step further, we get into AI agents, this idea of AI with true agency, which sounds a bit sci-fi, honestly. What exactly is an AI agent, and how does it work in this context?
Yeah, the term agent implies more autonomy. An AI agent acts more like a brain for a system. It processes information, it plans a sequence of actions to achieve a goal, it executes those actions, potentially using external tools, and then it determines if the task has been successfully accomplished. It's not just generating text in response to a prompt, it's actively trying to do something in the world.
And the book breaks down the key components that enable this agency. What are they?
Yes. Memory is crucial for agents to maintain consistency and personalization over time. Imagine an AI coaching agent remembering your entire life story and your progress week to week. This memory can be short-term, like the context window of a single conversation, or long-term, perhaps stored in a database and retrieved across many sessions.
Okay, memory makes sense. What else?
Tools. These extend the model's capabilities beyond just generating text. Agents need tools to interact with the outside world, maybe a web browsing tool for up-to-date information, a calculator or code execution tool for complex math, or APIs to interact with other software like your calendar or email.
And they need planning ability, presumably?
Absolutely. Agents often use intent classification to figure out the user's goal and then plan the right sequence of tool uses and steps to achieve it. These plans can be simple sequential steps, or more complex involving parallel actions, loops, or conditional logic based on intermediate results. Critically, good agents also need reflection and error correction. the ability to evaluate their own steps and adjust their plans if something goes wrong or isn't working. It's a much more dynamic, iterative process than simple generation.
However, agents also introduce new ways things can go wrong, new failure modes. What are some of the biggest challenges in getting them to work reliably in the real world?
Oh, plenty. They include planning errors, like selecting the wrong tool for the job, getting stuck in infinite loops trying to achieve a goal, or just creating a nonsensical plan. There can be tool execution failures, the API call fails, the website is down. And there are efficiency problems, like the agent taking far too many steps, incurring high API costs, or exceeding time constraints for a task. Building robust agents is still a significant engineering challenge.
Finally, let's talk about fine-tuning actually customizing these pre-trained AI models for specific needs. When would a company decide to go through the considerable effort and expense of fine-tuning a model versus just using prompting or RAG, and when would they opt not to?
Right, fine-tuning isn't always necessary or the best approach. The purpose of fine-tuning is typically to enhance domain-specific capabilities, like making a general model exceptionally good at medical Q&A, or legal document analysis, or a specific coding language. You might also fine-tune to strengthen safety guardrails for a particular application, or to really improve its ability to follow complex instructions or output data in very precise formats.
So you fine-tune when?
You'd consider fine-tuning when the off-the-shelf models, even with good prompting and RAG, just don't perform well enough for your specific demanding task. Or maybe you need to significantly reduce latency or inference cost, and a smaller fine-tuned model can achieve that. Or perhaps RAG isn't feasible, maybe because your proprietary data is too sensitive to be stored externally for retrieval.
And conversely, when would it not be the right move? When should you stick with prompting or argy?
Well, definitely don't try fine-tuning if you don't have enough high-quality training data. Often thousands, maybe tens of thousands, of curated examples are needed for effective fine-tuning. It's also probably not ideal if the cost or complexity of training and maintaining a fine-tuned model is too high for your resources. If the task can be solved effectively with just clever prompt engineering or a good argy setup, that's usually much simpler and cheaper. And critically, if you lack the in-house ML expertise to properly train, debug, and evaluate fine-tuned models, it can be a real struggle.
Training these large models, even fine-tuning them, is incredibly memory intensive, right? Because
Yeah.
of all the parameters, gradients, activations during training. The book mentions quantization as a key technique here. What does that mean for memory usage?
Quantization is basically a compression technique for the model's weights. Instead of storing each number parameter with high precision, like a 32-bit or 16-bit floating point, you reduce the precision maybe down to 8-bit integers or even 4-bit. It's like compressing a high-resolution image into a smaller file size. You keep the essential information, but it takes up much less memory space on the GPU and often speeds up inference too.
Does it hurt performance much?
There can be a tiny trade-off in accuracy sometimes, but often it's negligible, especially with newer quantization techniques. It's a key method that lets you run these massive models on much less powerful, more accessible hardware, opening up new deployment possibilities on edge devices or cheaper cloud instances.
This leads to techniques like parameter-efficient fine-tuning, or PEF, with methods like LoRa, which stands for low-rank adaptation. How does PEF make fine-tuning more accessible or practical?
PEFT methods like LoRa are fantastic because they make fine-tuning much more accessible and resource efficient. Instead of needing to update all the billions of parameters in the base model, you freeze the original model and only train a very small number of new parameters, often structured as small adapter layers.
So you're only modifying a tiny fraction of the model.
Exactly. This requires significantly less GPU memory and often less training data compared to full fine-tuning. It also dramatically simplifies serving multiple different fine-tuned models because the large base model stays the same, and you just need to load these small task-specific LoRa adapters, which might only be a few megabytes, on top of it. It allows for much more flexibility and efficiency in deploying customized models.
And there's an even more experimental but kind of exciting approach mentioned called model merging. What's that all about? It sounds a bit like Frankenstein's monster for AI.
Huh. Yeah, Frankenmerging is actually one of the terms used sometimes. It's an approach where you try to create new, custom models by combining multiple existing pre-trained or fine-tuned models. You might do this through simple methods like averaging the weights, linear combination, or more complex techniques that involve taking specific layers or parts from different source models and stitching them together, hoping to inherit the best capabilities of each parent model for a specific downstream task. It's still quite experimental, but it's a fascinating area showing how we might create highly specialized models without full retraining. So in practice, a real-world AI application isn't just one model sitting in isolation. It's usually far more complex. It involves a sophisticated architecture with potentially multiple models, various databases for context or memory, and a whole suite of tools, all needing to work together seamlessly.
Exactly. The book lays out some key architectural components you often see. Things like enhancing context with RC systems, implementing input and output safety guardrails, using model routers or gateways to intelligently direct user queries to the best or cheapest model for the job, and leveraging caching, like prompt caching for common instructions or results caching for frequent queries to significantly reduce latency and cost.
And then you need something to manage the flow, right?
Yeah, that's AI pipeline orchestration. It's about defining how all these different components, the router, the Argo system, the safety checks, the actual model call, maybe some post-processing work together in an end-to-end system. It's like being the conductor for a huge, complex AI orchestra, making sure everything happens in the right order and data flows correctly.
Makes sense. Now, beyond just building the thing, monitoring and observability become absolutely critical. These are essentially the eyes and ears of your AI systems once they're deployed. They're crucial for catching failures, things like hallucinations, security attacks, unexpected model drift, and also for identifying opportunities for optimization. It's really about ensuring your AI system is healthy, performing as expected, and delivering value 24/7.
And this goes beyond typical software monitoring, doesn't it? You need specific metrics tailored to AI. You need to track things that truly matter, like maybe the hallucination rate, your API cost per query, or the cache hit rates for your RGRE system. And ideally, you want these broken down by different segments, by user type, by application version, maybe even by specific prompt templates you're using.
Right, much more granular. Logs are still important, capturing those disjointed events that help you answer questions like, has this specific error happened before? But perhaps the most insightful, especially for debugging complex AI flows, are traces.
How do traces help?
Traces reconstruct the entire journey of a single user request as it flows through your potentially complex system, from the initial query, through the RAG retrieval, the prompt construction, the model call, any tool usage, the safety checks, all the way to the final response. Tools like Langsmith can visualize this entire chain of events, allowing you to pinpoint exactly where issues might be occurring. Maybe the wrong context was retrieved, or the model generated a bad response despite good context, or a safety filter blocked a valid request. Traces make debugging much easier.
And then there's drift detection. Why is that important?
Because the world changes. Drift detection involves continuously monitoring for changes in the input data users are sending, changes in the model's own behavior or output patterns, or even changes in the external APIs or data sources your system relies on. Catching this drift early helps prevent silent failures, where your application's performance slowly degrades over time without obvious errors.
Okay, now on to perhaps the most critical aspect for long-term success, especially in a competitive market. User feedback. The book argues it's more critical now than ever before in software. Why is that?
Well, user feedback is invaluable, not just for the traditional reason of guiding product development and identifying bugs. Crucially, for AI applications, user feedback provides proprietary training data for future model iterations. An early product launch that effectively gathers and incorporates user feedback can create this incredibly powerful data flywheel.
How does that flywheel work?
Your users interact, provide feedback, explicitly or implicitly. You use that feedback to improve your model or application. The improved application attracts more users or encourages deeper engagement, which generates more feedback data, allowing you to improve further. It creates this virtuous cycle that makes it incredibly hard for competitors who launch later without that rich user interaction data to catch up. Your users are literally helping you build a better product and a stronger competitive moat over time.
And when it comes to extracting conversational feedback, it's not always just a simple thumbs up or down, right? It can be more subtle.
Absolutely. There's explicit feedback, like thumbs up, down buttons, or star ratings. Easy to collect, but sometimes lacks nuance. But you can also gather implicit or natural language-based feedback.
Such as?
Things like a user ending a conversation abruptly might signal dissatisfaction. Explicit requests for clarification like, "Are you sure about that?" or "Can you try again?" suggest the model wasn't clear or correct. Users directly editing the model's response in an interface provides very specific correction data. And analyzing the overall sentiment of the user's language throughout the conversation also provides valuable insights into their satisfaction and potential pain points.
And clustering this natural language feedback, maybe identifying common themes that users complain about, like, the bot needs me to clarify my demand too often, or it gives irrelevant information, or it's factually incorrect on topic X, helps developers pinpoint how the bot is failing, allowing them to target improvements much more effectively rather than just guessing what's wrong.
Definitely. Now, when it comes to designing effective feedback systems, it's important to think carefully about when to ask for feedback. Maybe prompt for it at key decision points in a workflow, or after a task is supposedly completed, or specifically when something clearly seems to go wrong, like detecting a likely hallucination or experiencing a very slow response. You don't want to constantly interrupt the user.
And transparency is key here too, right? You should probably explain to users how their feedback will actually be used, whether it's just for aggregate statistics or to personalize their future experience, or even to directly train future versions of the model. This can motivate them to provide better, more thoughtful input if they know it matters.
Very true. And crucially, avoid asking users to do the impossible. Don't force them to choose between technical options they don't understand. Having an I don't know or not applicable option is vital to get genuine responses rather than random clicks.
And finally, you have to be aware of biases in the feedback itself. Design your feedback mechanisms to minimize known human cognitive biases, such as position bias, where people tend to favor the first or last item shown in a list, verbosity bias, favoring longer, seemingly more comprehensive responses even if they're wrong, or leniency bias, people being reluctant to give strong negative ratings. Sometimes, allowing for private feedback can elicit more candid responses than public reviews, too.
And one final important warning the book highlights are potential degenerate feedback loops. That sounds a bit ominous. What does that mean for AI systems relying on feedback?
It's where the AI's own predictions or actions start to influence user behavior and the subsequent feedback they provide, which then influences the next iteration of the model, potentially amplifying initial biases or creating unintended consequences.
Can you give an example?
Think of a simple video recommendation system. Videos that the system initially ranks higher get more exposure, leading to more clicks simply because they are seen more often. This click data is then fed back into the system, reinforcing its belief that those videos are indeed the best or most popular. This creates a popularity bias, a feedback loop where popular videos stay popular, making it increasingly difficult for new or niche content to break through, even if users might actually enjoy it if they saw it. It's a complex, self-reinforcing challenge that system designers have to be aware of and actively manage to prevent stifling diversity or amplifying unfairness.
Wow. So what we've really learned today from digging into AI engineering, building applications with foundation models, is that the journey from having a powerful base AI model to creating a truly successful, robust, and reliable application is incredibly complex, isn't it? It requires such deep consideration of data quality, model architectures, rigorous evaluation methods, clever prompt engineering, sophisticated deployment strategies, and just constant monitoring and iteration.
Absolutely. And perhaps the most crucial takeaway, for me at least, is that the future of AI doesn't just rest on the next big breakthrough in model size or raw capability alone. It fundamentally depends on how meticulously we engineer these systems around the models, how smartly we gather and use data, especially user feedback, and how effectively we integrate insights from you, the user, into an ongoing cycle of improvement. It's really a testament to human ingenuity in adapting to and shaping this new technological landscape, and it's where so much of the real innovation needs to happen now.
Indeed, the practical application of AI, turning that cutting-edge research into tools that genuinely solve problems, are safe and actually improve lives. That's where the real magic and, frankly, the real challenges still lie.
Well said. And for those of you listening who are eager to dive even deeper into this world of AI, maybe to learn more about the tools available or even explore how you might leverage AI yourself, perhaps to create value or even make money, we definitely encourage you to visit easymasterai.com. They offer a great range of resources to learn about AI and discover tools that can help you navigate this space. That's easymasterai.com. Thank you so much for joining us on this deep dive today. Until next time, keep exploring, keep learning, and definitely stay curious.